Okay, we're talking about electrolysis. We discussed electrolysis in the molten state. Okay, you take an ionic compound, you melt it so that the ions are released, and then you run electrical current through and you make your electrolytic cell. We use the down cell. That's how chlorine is commercially produced. But the downside of the down cell is that it takes a lot of energy to melt ionic compounds and to keep that heat, and it's not real practical sometimes. So another alternative to separating ions in an ionic compound is to put it in water. We dissolve it in water. Now the problem with having an electrolytic cell in water is that the water itself can be oxidized and reduced. And so what happens is we have competing half reactions, all right? The ion that we're trying to reduce will compete with the water being reduced, and whichever has the highest reduction potential will be reduced first, all right? So the only thing that's going to be reduced in water is those that have a higher reduction potential than water. Conversely, what we're trying to oxidize had better have a lower reduction potential, because a lower reduction potential correlates with an ease of being oxidized. Because remember, all of those E values are written from the perspective of reduction. All right, so we have two things going on, so let's see how that works. I'm going to do a couple examples here. You might want to pause your video, see if you can work through them, and check to see how I did it. But let's take copper 2 bromide, and we're going to put it in water, all right? So remember, electrolytic cell, the opposite happens of what normally does. So normally, metals are oxidized and nonmetals are reduced. So what we're going to have, okay, what we're going to have in an electrolytic cell is this copper 2 plus 2 electrons going to copper, all right? And then what's going to be oxidized then is the bromine going to elemental bromide, all right? So that is what's going to happen in an electrolytic cell. All right? Because the opposite, we have artificially charged electrodes. This positive will be attracted to the negative. This negative will be attracted to the positive. So it's important that you know which it should have done correctly, metals usually being oxidized and nonmetals usually being reduced, and then make it the opposite. However, as we said, we have to worry about water being either reduced or oxidized, all right? And that's where you have to remember which half reaction is water being reduced and which half reaction is water being oxidized. And I said the one that starts with oxygen is water being oxidized. So that's what it will compete with. All right, so we have this is what will happen if water is oxidized before the bromine, all right? And this is what will happen if the water is reduced instead of the copper. So now let's look at their E's from that reference sheet that I handed out to you, all right? Well, copper has an E of plus 0.34 volts. Water has an E of negative 0.83 volts, all right? Okay, so which one has a higher reduction potential? Remember, this is what's going to be reduced. It's copper. So we actually will get the copper being reduced in an aqueous solution because it has a higher reduction potential than the water. All right, now let's go over and look at this. Bromine has a reduction potential of 1.07 volts. Water has a reduction potential when it's oxidized of 1.23 volts. All right, now we said to be oxidized, you have to have the lower reduction potential, because a lower reduction potential will correlate to the ease at which it's oxidized, because oxidized is reverse. So which one has the lower reduction potential? Well, bromine does. Okay, so it will be oxidized before water's oxidized. So this would be a situation where in an aqueous solution you would get copper reduced and you would get bromine oxidized, and the water would stay unreduced and unoxidized. Okay? Let's look at another one. I'm going to leave the water up here because that's not going to change. Lithium iodide. We're going to put lithium iodide in water. The water breaks apart the ionic bonds, and now we have these ions. All right? And normally we said that the metal is oxidized. So in an electrolytic cell, the opposite's going to happen. So we're going to either have lithium plus one electron going to lithium and being reduced, or we're going to have the iodide being oxidized. Well, and, all right. All right, so we look on our reference sheet, and these values would always be given to you on the test. They're not going to give you a whole table, but they'll cut out the applicable reduction potentials. All right, and for lithium, we see it has a reduction potential of E equals a negative 3.05 volts. And that makes sense because lithium is a group 1 metal. It's not going to be reduced very easily. All right, so water actually has a higher reduction potential. So what this means is in an aqueous solution, water will be reduced before that lithium. Nothing's going to happen. You're not going to get metallic lithium in an aqueous solution. All right? So let's go over now and see about iodine and water. Iodine has a reduction potential of plus 0.53. Okay? Remember we said when we're looking at competing oxidation, it's the one with the lower reduction potential. Okay? So iodine has a lower reduction potential than water. That means it'll be easier to oxidize, right? So you would get that. In this, if you put lithium iodide in water, then you would get iodine, right? But you would not get lithium. So this would be an example of one where you get one part of your ionic compound oxidized, but the other would not be reduced. All right? So once again, with an electrolytic cell, it is important to first realize what is the normal outcome. The normal outcome is that metals are oxidized and nonmetals are reduced. In an electrolytic cell, you get the opposite because you are artificially charging those electrodes. So you have something different going on. Your positive ion is going to go to the negative electrode and become reduced. All right? So you have your ionic compound. In water, you do the reverse of what normally should take place. And the reverse is that my metal is going to be reduced and my nonmetal is going to be oxidized. And then you compare it because water gets involved. What will happen to the water? Well, if water is going to be oxidized, it's going to look like this. All right, it's going to start with oxygen, oxygen, oxidized. If water is going to be reduced, it looks like this. And they will give you those equations. Those equations will be on your reference sheet. You just have to remember which one is competing with the reduction half reaction and which one is competing with the oxidation half reaction. And then you compare the E-values. For reduction, whichever one has the highest reduction will be reduced. For oxidation, whichever has the lowest reduction will be oxidized. All right? So those are the things. Electrolytic cells in an aqueous solution then are a little bit more complicated than electrolytic cells that are just take the ionic compound and have it melted. All right? Okay, so that's the end of this lesson.